Testing. Okay, good morning. Once again, we can see that my computer is fighting me. Let's hope I've won the battle. Okay, so let's get started. Excuse me, please quiet down. All right, so exam 2 is coming up. So next Friday will be the first of 2 review sessions. So they're same time, same location, same facilitator for each one. So next Friday at 4, it'll be Brian. Study materials have been posted on Canvas for a while. As we get closer to the date, then I'll think about posting the solutions to the practice exams and the solutions to the review worksheets. So please, come prepared to the review session so that you get the most out of it. All right, so sort of a global overview of where we've been, and where we're going. So previously, we've shown that we can write the system partition function in terms of the particle or molecular partition function. We've been limiting our discussion to ideal gases. In the homework that you turned in today, and we've stated this already in class, the particle partition function is the product of the partition function for each of the energy modes that are available to our particle, right? And then we've explicitly derived translational, rotational, vibrational, electronic for our molecules. So once we have the partition function, then we can take the partial of the natural log with respect to beta. That's going to give us a path to the energy of the system. So we've got the energy, translation, rotation, vibration of the 0 point energy, energy above the 0 point, and then there's our electronic energy. Once we have the energy, we can take the derivative with respect to T. That's the definition of heat capacity. And then we know what the heat capacity is for our ideal gas. All right? So basically, we're able to calculate a lot of information out of these partition functions. Right? What's sort of interesting, at least to me, is that because we have explicit partition functions for each of the different energy modes, that means we can calculate energy of our system that's due to each of those different modes, and we also can determine what the contribution to heat capacity is for specific modes. All right? And then we've also pointed out that we can calculate the probability of being in a given rotational state, electronic state, etc., using the particle partition functions. Okay? Some things that we need to remind ourselves in moving forward. So you probably, since junior high, have heard the definition of energy, the capacity to do work. All right. So the property of matter and radiation is manifest as capacity to perform work, including causing motion of the molecules. So if you think about causing motion of molecules, that's getting them to move faster, which is increasing their kinetic energy, and that's talking about adding heat. All right. So heat drives work. All right, so it's very important to us. We're also going to be talking about isotherms. We're limiting our discussion at this point to ideal gases. So that means that when we're talking about isotherms for the upcoming chapter, we're basically talking about temperatures above the critical temperature. All right, so and it's ideal gas. Actually, let me go ahead and just take a moment to write that down then. So if we're talking about an isotherm, and we think about ideal gas law, PV equals nRT, right? And that means that this is a constant. And you may recall from general chemistry that when you have an isothermal process, you can write P1V1 equals P2V2, right? And that's just restating what holds true for an isotherm, right? We're also going to have to talk about some unit conversions. So just a reminder, joules is kilograms meters squared per second squared. Pascal is the SI unit that's associated with pressure. 1 bar is 10 to the 5th pascals. And then pascals is a kilogram per meter per second squared. So we're going to be using that conversion to do a conversion down the road. And then just a reminder, I like to remind everybody of some things that I know are usually stumbling blocks. We've previously defined the change in the enthalpy as Q sub P. So that's constant pressure, energy transfer in the form of heat. Okay? All right. So the very last thing that I covered on lecture on Wednesday was looking at specifically for ideal gases. So we have the energy for a monoatomic ideal gas, a linear ideal gas, a nonlinear ideal gas, right? So we've seen all that before. If we look at this, what we see is that it's a function of N, T. We've got Kb in there. We've got these vibrational temperatures. We have rotational temperature. Well, I guess we don't have rotational temperature, but that's all right. But for a given molecule, a system of molecules, these are constants, all right? And so if anything changes, it's only going to be temperature and the number of moles that determine the energy. Does that make sense? Because everything else is a constant, right? And what we've stated previously then is that for an ideal gas, the energy of our system is a function of temperature and the number of particles. And if we hold the number of particles constant, temperature is the sole determinant of a change in the energy, right? So if we have a system where we don't change the temperature of the ideal gas, holding the same the number of molecules constant, that means that delta U is equal to 0, right? All right, so some questions that we're going to talk about today. We're going to do the next math chapter. We're going to talk about partial differentiation. Hopefully for most of you, this is review. We're going to talk about something known as a total differential or a total derivative. And then from there, we're going to introduce cross derivatives. How many people have heard of cross derivatives before? All right, so some of you have. How many is it new to? All right, so it's a second derivative. It's pretty straightforward. And then from there, we're going to go to exact and inexact differentials and what the significance to thermodynamics of having those types of differentials. And then from there, we're going to move into a discussion of the first law of thermodynamics. Because that's important, let's go ahead and write that out. So the first law of thermodynamics, and all of the thermodynamics laws can be written in a number of ways, but what we can say is that the change in the energy of our system, which is the same as delta U, which you've seen as internal energy previously, is given by energy transfer in or out due to heat and energy transfer in or out due to work, okay? All right, so that's a statement of the first law of thermodynamics, right? We're going to be talking about pressure volume work. So basically, this is talking about compression or expansion of a gas, right? And then we'll do some conversion factors and talk about path functions and state functions, right? We're going to use this concept of a reversible process. So I wanted to just talk a little bit about this at the outset. How many people recall hearing about reversible processes before? All right, so a number of you. All right, so this is sometimes a difficult concept to wrap your head around. For a reversible process, basically what we're saying is that if we're changing from one state to the other, we're doing it incrementally so that we have an incremental change every step of the way, that if I reverse it, I go exactly to where I was before, all right? Does that make sense? All right, so sometimes that's not that easy to think about, so I tend to think of it as, let's say I'm moving from here to the other side of the room. I can do that incrementally, right? I go back, I'm back where I was. If I'm standing on a cliff edge, right, and I take an infinitesimal step out off that ledge, if I step back, do I get there? No, all right? So that's an irreversible process. Going out a window and falling to your death is irreversible, all right? So whenever we do these reversible processes, that means that our system is at equilibrium every step of the way. And at the practical level, this is something that is not common, right? Because it takes, for me to go reversibly to the other side of the room, it's going to take me forever, right? Okay, but it's a good theoretical limit to keep in mind, okay? All right, so last time we met, we talked about the impact of changing one of our variables on a function of those variables, all right? And we've basically said that if I want to know the change in my function due to changing one of the parameters that it depends on, I'm going to take the derivative of the function with respect to that variable times the change in the variable. And if I want to know an explicit delta f, I need to integrate both sides, right? But this tells me for an infinitesimal change in x, this is the infinitesimal change that results from in the function, Okay, and that's a pretty important concept for this next section. All right, so math chapter D, we're going to talk about partial differentiation. Okay, all right, so a partial derivative, all right? So basically what we're saying is we're going to look at a change in a function that depends on multiple variables. So I'm going to say x, y, z, etc. And the partial derivative says all I'm going to do is I'm going to look at how that function changes if I choose one of those variables. So it's going to be the derivative of the function. I'm going to choose it to be x, right? And that means that in order for me to do the differential, I have to hold y and z and all of the other variables constant. Okay? So that's a partial derivative. So it's how the function changes due to an infinitesimal, and I don't know if I know how to spell infinitesimal. I know I don't know how to say it, change in one variable. Okay? All right. And because it's Friday, we have a gift. Are we excited? All right. It is a group gift. What I would like you to do is start with the very first question. You can work in groups of up to 4. Please make sure your name's on there. And we will work on this one as a group. So let's not. So you guys basically get credit for being here today, right? Did I give you guys one? I gave you 2? Okay. All right. And you guys are set? Okay. Oops. All right, so let's go ahead and talk about the first one. So I'm basically telling you that there's this thing called a coefficient of thermal expansion. It tells us how some material changes due to a change in temperature. Its definition is 1 over V times the change in V due to a change in T, holding the pressure constant. This is absolutely general, right? This could be utilized for a solid, for a liquid, as well as a gas. We're going to say, for our example, we want to do the expression of thermal expansion specifically for an ideal gas. So I come to our equation of state, PV equals nRT. I know that I need to take the derivative of V with respect to T. So I'm going to rearrange for volume. V is equal to nRT over P. That gets plugged into the and this is where we do a partial differentiation, partial derivative, right? So I'm taking the derivative with respect to T, holding everybody else constant. That gives me nR over Vp. Now, if you look at that and compare that with the ideal gas equation, what's that the same as? Anybody? It is the inverse temperature. Who said that? That's like so candy-worthy. You can take the box home with you for the weekend. Right. Just kidding. Just kidding. All right. So that's 1 over T. All right. And if you think about what you know about ideal gases, you know that if you're holding the number of particles and the pressure constant, the only thing that determines the volume is the temperature, right? Okay, so that's an application of partial differentiation. So many of the properties of a thermodynamic system that we're interested in depend upon more than one variable. So then we can ask the question, how do I determine the change in this property due to changes in the individual variables that determine that overall thermodynamic function? Right? In order to answer that question, we do what's called a total derivative or a total differential. So I'm going to say that I have a function of x and y. Right? I could choose additional, but for simplicity, I'm going to hold it to 2. And basically what we can say is that the change in our function, because it depends on x and y, will be determined by changes in x and changes in y. Right? So I'm going to write over here dx and over here dy. Okay? All right. And then if I want to translate from an infinitesimal change in x to a change in the function, I need to know how that function changes with x. So that's the derivative, df dx. Partial of our function due to a change in x holding y constant. Right? And my next term will be df, d, help me out, dy, and now I hold the other variables constant. Okay? All right. And so basically what this says is this single equation tells me that I can determine how the function responds to a change in x and how it responds to a change in y. All right? And of course, looking further down the road, in order to get a delta f, I'm going to have to integrate both sides. Okay? All right, and then word-wise, this basically tells us how function responds to small changes, because that's easier to say than infinitesimal, in multiple variables. So dx, dy, right? And so basically, this is global, and it tells us, all the all the variables that contribute to our system, our thermodynamic property. This gives us the relationships. Okay. All right. Let's see. So what I would like you guys to do is, so this is a separate question from the previous one. All right. Just want to make sure. I'm telling you that in general, pressure depends upon the volume and the temperature of the system. All right? And so I want you to write a total derivative for the pressure, or a total differential. All right, let's go ahead and talk this one through. All right, so again, global perspective on this. Pressure depends on volume and temperature. So this first term, because I have an infinitesimal change in temperature, this is going to be how the pressure depends on the temperature, dP dt. All right, and I'm going to hold the volume constant. So dP dt. All right, my next term, because I'm looking at the impact of changing the volume on the pressure, this is going to be dP dV. Okay, and I have to hold my temperature constant. All right? And what I've derived here is totally independent. This works for any system. As long as I have an equation of state that relates the volume and the temperature and the pressure, I can plug that in there. All right? So I could do it for a solid, I could do it for a liquid, we're going to do it for a gas. So let's go ahead and do the next part of this. So we have the total differential for pressure in terms of changes in temperature and volume. So now I'm going to say, let's assume that we have an ideal gas. So that means we need to look at dP dV for an ideal gas and dB dt for an ideal gas. right, talking this through, pressure is equal to nRT over V. That means I'm going to take the derivative of the pressure with respect to T, with respect to V. What's the derivative of nRT over V with respect to T? Holding volume constant. nR over V dt, right? Next one's a little bit more complicated, right? In this case, we're holding the temperature constant, so nRT as a constant comes out in front, so this is the derivative of V to the minus 1 with respect to V, right? So that's going to become minus nRT over V squared dV, okay? All right, so for an ideal gas, I can calculate the change in the pressure by integrating from T1 to T2 and from V1 to V2, okay? So this is the impact on the pressure due to a change in temperature. This is due to a change in volume. Make sense? Okay, so let's scroll back a little bit, all right? So if we come back to our total differential, what we see is that we've got the derivative of the function with respect to one of our variables. And here I've got the derivative of the function with respect to the other variable. The cross derivative is when I take the derivative, the result of this differentiation, I take the derivative of that with respect to the other variable, right? So it's easier to just see it. So the cross derivative of df dx holding y constant will be the derivative with respect to y, and now I'm going to hold x constant. Okay? So it means that I'm taking a second derivative, and I'm taking it with respect to the other variable, right? Writing this in shorthand, this is the same as d squared f dy dx, right? So again, the way we read this, I take the derivative of the function with respect to x, and then I take the result of that and take the derivative with respect to y, okay? And then my other differential will be d squared f, and then I take the derivative in the opposite direction, so it'll be dx dy, right? And so there'll be the derivative of the function with respect to y, holding x constant, and then the derivative of that with respect to x, holding y constant, okay? All right? Why don't we take a moment to do those before we talk about the implications, all right? So we will see that this is going to be important in determining whether we have a state or a path function, right? So that means basically I want to calculate, or I want to determine what the cross derivatives are, all right? So my first one will be d squared p dt and then dv, okay? All right, so if that's the first one that I choose to do, that means that I'm going to take the derivative of the pressure with respect to T first, which is what I've done here. And that means I need to take the derivative of this with respect to V, okay? So the derivative of nR over V with respect to V holding temperature constant. That is our cross derivative, right? And n and r will be constant, so they come out in front. And then I've got the derivative of v to the minus 1 with respect to v. That's going to be minus, help me out, what's in the denominator? V squared. All right? Does that make sense? All right, I'm going to do the same thing for the other cross derivative. So it'll be the second derivative of the pressure. Now, we're going to start with the derivative with respect to v. And then we're going to take the derivative with respect to t, all right? So in this case, that'll be the derivative of minus nRT over v squared with respect to t, holding the volume constant. And what's the result of that? Minus nR over v squared, okay? All right, and one of the things that we see is that these come out to be the same in this particular example. Right? So I think what I want to do then is talk about the mathematical terminology here. If these cross derivatives are equal to each other, then the differentials are called exact differentials. And in the homework, you'll see examples where you take the cross derivative, and we'll see some examples down the road where they're not equal to each other, right? And those differentials are therefore not exact or inexact. Okay? All right, so the implications that this has for us in thermodynamics is the difference between a state function and path function. How many people recall state and path functions? Right? So if I told you, so let's compare two things. Let's say one thing is the distance from this room in Ames to the Capitol building in Des Moines. That's one thing, right? The other one is I'm going to travel from here to the Capitol. What's the total distance that I travel? Which one of those is a state function? Well, let's ask this question. Can I get to the state capitol by going to Minneapolis first? I can, right? So if I don't know the path, right, I could have gone to New York City on the way and then come here. So the distance traveled by me is a path function. You need to know how I did it, right? But if I said the absolute difference in distance between the Capitol building and where we're sitting right now, that's fixed. Does that make sense? Okay? All right. So that's a state function. Okay? All right, so connecting that with our differentials, right? In this case, we don't care about the order of the differentiation. No matter how I do it, it's the same. Here, the way that I do it has an impact. I get a different result. So which one of these, exact or inexact, is going to correlate with a state function? Exact, right? And an inexact differential will correlate with a path function. Right? And if we look at what we've just shown, is that we have our pressure, dP, that's an exact differential. Right? What does that tell me about pressure? Is it a state function or a path function? Okay? And that should make some sense, because if I have a gas at one pressure and a gas at another pressure, we don't know how we got there, right? But the difference between those two pressures is going to be the same, right? Does that make sense? Okay. All right, we'll come back to that last question in a minute, right? So here we're just going to go through some dotting I's and crossing T's. If we have a state function, if we have an exact differential, then when I integrate dx, that's going to be x2 minus x1, all right? So that's equal to delta x. If I have a path function, I can't make that statement, right? I need to know how I'm going. So they're not equal to each other, all right? And what we do in order to distinguish so that we know whether this integral is a delta or not, is we use different symbolism for the two differentials, right? So if I say dx, that means we have an exact differential. Right? And if I have delta x, then it's an inexact differential, right? So we're going to show that these are all state functions, all right? And so that means that we will see dP, right? We'll see dP, du, dH, dt, all right? We will also show that work and heat are not state functions. They're path functions. And so when we go to look at the incremental infinitesimal change in work and heat, we use delta, so dW and dQ, right? The other one I'm going to add in here is heat capacity. We will see that that is a path function, okay? Make sense? All right, we already talked about the difference between state and path functions, so we don't need to hit that again. All right, let's go back and answer this last question. All right, so this is an important tool that we're going to see that we can use down the road. All right, so I just wanted to get us used to it now. So we will eventually show that the change in the energy of our system is given by TdS, where T is temperature, S is entropy. So this says temperature times the infinitesimal change in the entropy minus P dV. Okay? All right, so when I step back from this, I can look at that equation, that differential equation, and that equation tells me that changing S and changing volume will impact the energy of the system. So I can say that U is a function of S and V. All right? And as soon as I recognize that my function depends upon entropy and volume, then I can write a total differential. Right? So I can say du is equal to how the energy of the system responds to a change in the entropy times the change in the entropy. And what am I going to hold constant? I'm going to hold volume constant in that. And then in addition to that, I can say this system energy depends upon the volume with this second term. Why are you not doing this? And in this case, we have to hold the entropy constant, right? So as long as we know that the energy depends on these variables, I can write this total differential. Now what I can do is I can say, let's look at this and compare it with this differential equation, right? We see that I've got ds here and ds here, and we have dv and we have dv. That tells me that du ds has to be the same as, it has to be the same as the temperature, okay? And du dv has to be the same as negative p, all right? So we're going to be utilizing this a lot down the road. One of the things that we step back and look at, we say, oh, we know the temperature is really easy to measure. Pressure is really easy to measure. And if I know this pressure, that means I also know how that energy of the system responds to a change in volume, right? That's not quite as easy to measure directly, right? Okay? So that's an important tool that we're going to be utilizing down the road. Okay, so chapter 5, this will be the first law of thermo. In the announcements that I sent out on Wednesday, I sent some links to some background information. If you have your Gen Chem textbook, the chapter on thermochemistry is good foundational for this material, as well as parts of the thermodynamics chapter. Okay? All right, so just to sort of set the stage, what we know is that classical thermodynamics has all been determined in the mid to late 1800s based upon empirical evidence or empirical observation. Basically experimental. Okay? And when we talk about laws, we recognize that laws don't tell us why things occur. They just summarize what occurs. All right? So the laws of thermodynamics basically summarize the experimental observations. The result of the experiments that were done were summarized in 3 fundamental laws. We don't know of any exceptions, which makes them pretty darn important. And then the first law of thermodynamics is basically talking about conservation of energy. All right, so it's extension of the law of conservation of energy to a macroscopic system. So there's a number of ways you can write this. One way we can write is delta U of the universe is equal to, can anybody tell me? If we say that energy is conserved, what's the change in the energy of everything got to be? It's got to be equal to 0, right? Now, we're not often going to be talking about the universe as a whole. We're going to be focusing on a chemical reaction or maybe a vessel that has some gas in it, right? We call that our system. Delta U of the system will be exactly equal to the energy transferred into or out of the system, and there's only two ways to transfer that energy. One is to do it via heat, Q, and the other is by doing work on it or having it do work. Okay? All right. A couple things. Again, this emphasizes the importance of work. So this is from my little tiny beach read on thermodynamics. Work's the primary foundation of thermodynamics. All of this heat transfer we can think of as being equivalent to work. All right? And I did want to, so one of the things that, because you've been taught this for a while, it's obvious to you, right? But there was a time when people didn't recognize that work and heat were transferring the same stuff, right? So, in the mid to late 1800s, a guy named Joule, recognized that, did these experiments where he basically did some work, ran a paddle wheel in here, measured the temperature change in here, right? And what he determined, in conjunction with some other people, Carnot we'll talk about later, is basically that we're transferring this thing called energy, and it's going to be in terms of heat and work, and they are equivalent to each other, right? Okay, but it wasn't obvious for a long time. Okay, all right. So again, the beginning part of this chapter, we want to set the ground rules, talk about sign conventions, and how we define systems so that we don't have any confusion. Right? So we've determined that the modes of energy transfer between what we're calling a system and what is not the system, the surroundings, will be heat, Q, and work, W. We're going to see very quickly that these guys are path functions. Right? The way that you do it determines the heat and the work energy transfer. Right? And again, we're going to be talking about enthalpy, Q sub P, energy transfer in the form of heat, at constant pressure. Right? And here I just want to add, at constant pressure practically means that we're just doing this process open to the atmosphere. Okay? Okay? All right. Section 5.1. What the hell is it? Oh. All right, so section 5.1, we're going to be talking about pressure volume work. Or PV. Right? And again, because we're talking primarily about ideal gases, this really is discussing expansion and compression of a gas. Okay? All right. So we want to make sure that we understand what we're focused on, all right? And so in thermodynamics, we basically say everything, the universe consists of two parts. One part is what we refer to as the system. The other part is the surroundings. Right? And you need to carefully define what your system is, right? And we'll see why that is in a moment, right? So for our, initial examples, our system will be a gas, right? But as you've seen back in general chemistry, you can also think of the system as being a reaction, right? It could be what's in a beaker. And then if you're thinking about engineering, then you might be thinking about an engine as being your system, right? But whatever it is, it needs to be defined, right? And then the surrounding is everything other than the system. So I'll just say everything else. Okay? All right, so do a little diagram here. I'm going to say that this little box is my system. All right? That means that everything outside of that box is the surroundings. All right? And this is why it's really important that we define the system. Okay? So let's say that my system absorbs heat from the surroundings. Right? So heat's added to the system. If that's the case, we expect the energy of the system to increase, right? So we need to talk about signs. So heat going into the system is going to be a positive value from the system point of view. Does that make sense? And if we're talking about the energy change to our system, it's going to also be positive, right? Because we've dumped energy in. Right? But from the surroundings point of view, what's the sign of Q? It's got to be negative, right? Because the net sum has to be 0, right? And so it's going to be exactly the same heat transfer as went into the system, but it's going to have the opposite sign. Okay? Right? And this just emphasizes the importance of knowing the boundaries of your system. Right? Because if I ask you what the heat transfer in or out of something is, you need to know what the system is versus the surroundings. Because if it's the surroundings, you're going to give me an opposite value. Okay? Make sense? All right. And then, of course, we can say that if we take heat out of the system, that means we have a negative value. We're going to see a negative change. If that's the only thing that happens to our system, that means its energy has decreased. Right? And because it's putting heat into the surroundings, the heat transfer to the surroundings is now going to be positive. Okay? Same thing happens with work, right? Yeah? Oh, I screwed up. Yes. Could you pass the box to that next table? Thanks. Okay? No violence, no violence. All right. So we've said that there's two ways to transfer energy. One's to, through heat transfer of energy. We also can do it through work. All right. So if my system has work done on it, right? If I'm doing work on it, what do you think that's going to do to the energy of the system? Is it going to go up or down? It's going to go up. Right. So delta U, the system goes up. That also tells me that the work is positive. All right. And if you think about it, the work's done on the system by whom? The surroundings. And so the surroundings have to have lost energy in doing the work. Okay? All right, and then here I have a little typo, so this would be W. So if we do work on the or by the system, that means the system is expending energy to do work. We expect this to be a negative number. The system energy will decrease, and the surroundings energy, because the work's being done on the surroundings, will be positive. Okay? All right, so it's very important to keep the sign convention, all right? Okay, and of course, knowing where your system is determines what the sign is. Okay, so now what I want to do is I want to just talk about work in terms of expansion and compression, okay? So let's say I have a gas, and I have an external pressure on it, right? And that external pressure is constant. Whoops, where'd my phone go? Okay. if my gas, whatever I do to it, causes this to go up, that means I'm pushing back the atmosphere, right? Does that make sense? So in expansion, is my system doing work or is work being done on it? It's doing work on the surroundings, right? So work of the system is going to be less than or greater than 0. It's going to be less than 0 because it's expending energy to do the work. Does that make sense? All right? That's very important. And of course, if I reverse the process, if I go from this stage to this stage, I've done a compression. And that means that I've done work on the system, and that means that the work from the system point of view is positive. Okay? That's a clean place for us to stop. Again, you guys, I'm ahead in your lecture, so I'm going to try to get caught up this afternoon in at 1:10. Have a nice weekend.